Hello there, amazing students and all the lovers of chemistry out there. I'm so excited to be here with you once again today on this episode. My name is David, and as always, you know that what I do here is take the mystery out of chemistry so chemi can make history. All right, so far it's been a series on the concept of stoichiometry in chemistry. Our previous video was an introduction into the concept, and today we're going yet again deeper into what it is all about. So, today we want to talk about the mole concept and Avogadro's number in the subject of stoichiometry. So, sit back, relax, fasten your seatbelts, and enjoy every bit of today's show. So, let's introduce this bad boy very quickly. The mole concept is a fundamental idea in chemistry. It allows scientists to count and measure atoms, molecules, and ions in a practical way. Now, let me not get ahead of myself. Let me explain something very briefly. One of the facts about atoms, and by the way, an atom is the smallest part of an element that can act chemically like that element. Now, one of the facts about atom that we know today is that they are so small they cannot be seen with our natural eyes. So there has to be a way that we can count these things without having to do that with our natural eyes. One of the ways that has made this possible is the concept of moles. Now, since individual atoms are too small to be counted one by one, the mole concept provides a standard unit to quantify them. Now, Avogadro's number links microscopic particles to measurable quantities, making chemical calculations possible. Now, let me use a concept that we can all relate to. The bolts that fasten the tires of your car and that hold them in place. If you try to knot them in place using your hand, it will be an impossible task. But then there are some tools that help you to do that. For instance, your spanner and your wrench. When you use a spanner and a wrench, it becomes easier to tie the bolts that hold the tires of your cars in place. In much the same way, we cannot count atoms, we cannot count molecules, we cannot count ions with our normal eyes. In fact, we can't even see them. So there has to be some tools with which we can count them in a practical way. And that is where the concept of moles and Avogadro's number come in. So let's proceed. Let's talk about the mole before we move on to Avogadro's number. What is a mole? A mole. A mole is spelled in two ways. There are some scientists that spell it as MOLE, some spell it as MOL. Whichever way you prefer is absolutely fine. A mole is the standard international unit. SI stands for Standard International. It is the standard international unit for measuring the amount of a substance. It represents 6.022 times 10 raised to the power of 23 particles. And those particles can be atoms, molecules, or ions of that substance. Now, here is what we mean. In chemistry, whenever we mention the term 1 mole of a substance, we are simply saying 6.022 multiplied by 10 raised to the power of 23 atoms, molecules, or ions of that substance. Now, you will notice with me that when I say atoms, molecules, or ions, I said earlier on that they are not things we can see or count with our physical abilities or with our natural eyes. So, therefore, there has to be an SI unit or a standard with which we can count them. So that is where the concept of a mole comes in. So a mole simply quantifies them in a practical way. So whatever the element it is that you are dealing with, 1 mole of a substance contains 6.022 multiplied by 10 raised to the power of 23 representative particles. That is the Avogadro's number. All right, now, why did we even pick the concept, or why did we pick the number 6.022 times 10 raised to power 23? First of all, the number was determined experimentally. They didn't just pick it haphazardly, okay? It was determined experimentally by the scientist Amedeo Avogadro, and it was later refined by scientists. This number also allows us to relate atomic scale measurements to macroscopic quantities. Macroscopic quantities like grams, liters, and etc. Now, here are some examples of 1 mole. For instance, 1 mole of hydrogen atoms, H, contains 6.022 times 10 raised to the power of 23. For instance, if I say, David, measure for me 1 kilogram of rice. Measure for me 1 kilogram of rice. Now you know that 1 kilogram is made up of 1,000 grams. So I'm simply saying count 1 gram in 1,000 places and bring them together. In much the same way, when we say 1 mole, we are saying 6.022 times 10 raised to the power of 23 particles all coming together. I hope that is clear. In the same way, 1 mole of water molecules makes up 6.022 times 10 raised to the power of 23 molecules of water. 1 mole of sodium chloride also makes up 6.022 times 10 raised to the power of 23 formula units of sodium chloride. So whatever it is we are dealing with, whether it's an atom, whether it's a molecule or an ion, once we mention the term 1 mole, we are referring to 6.022 multiplied by 10 raised to power 23. Now let's talk about another concept, Avogadro's number, understanding it. The Avogadro's number is a conversion factor that helps us to relate microscopic particles to measurable quantities. This number is so important because it helps us to convert. Now, I'll be showing you some of those things shortly. Look at the first example. First question says, how many molecules are present in 2.5 moles of water? How many molecules are there? Now, if you are to do this with your natural abilities, you know it is not possible because you can't even see molecules with your natural eyes. So what do we do? First things first, we are to remember that we've been taught previously in this video that 1 mole of a substance contains 6.022 times 10 raised to the power of 23 particles. It therefore follows, we can write this mathematically. 1 mole is equal to 6.022 times 10 raised to the power of 23. And we were asked how many molecules are contained in 2.5 moles. Therefore, we can now say 2.5 moles will be equal to X number of molecules since we do not know the number of molecules that are contained. Following this pattern, we can now cross multiply. If we cross multiply, X goes to the left side and then 2.5 multiplies 6.022 times 10 raised to the power of 23. When we do that, we get the answer. Our number of molecules will now be 2.5 moles times 6.022 times 10 raised to the power of 23. That gives us 1.506 times 10 raised to the power of 24 molecules of H2O. Therefore, 2.5 moles of water contain 1.506 times 10 raised to the power of 24 molecules. I hope that is clear. We'll have more examples to come. Now let's talk about that brings us to the concept of molar mass and molecular weight. Now in chemistry classes, possibly in your school or some other places where you happen to chance upon the concept of chemistry, you may have heard this term being thrown around, molar mass, molecular weight. What is it? What does it mean? Now, as the name implies, now there are two words that make up this term, molar and then mass. So in a layman's definition, let me define it basically as simply as you can understand. It is the mass that has to do with moles. As the name implies, molar mass is the mass of 1 mole of a substance expressed in grams per mole. So when you measure 1 mole of a substance, all right, that mole, whatever the mass is called its molar mass. It is calculated by adding up the atomic masses of the elements in a compound. Now you can see on the screen, I have some examples of the atomic masses of some elements, carbon, magnesium, and chlorine. Now, if you have a compound is simply what is produced when two or more elements combine together chemically. So for instance, let's say I have water, H2O. Whenever I measure the atomic masses of the individual elements and I add them up together, that will give me the molar mass of water. And we'll do some examples in a jiffy. Now look at this. This question says calculate the molar mass of water H2O. Now, first things first, you need to know the relative atomic masses of all the elements that are present in the compound water. What are the elements present? We have hydrogen, and hydrogen has the relative atomic mass of 1.008 grams per mole. We have oxygen as well. Oxygen has the relative atomic mass of 16 grams per mole. So what do? We have the formula H2O. H there stands for 1.008. So we put 1.008. How many atoms of H do we have? We have not one, we have two. So therefore we simply multiply it by 2 because you can see at the bottom of H there is a subscript of 2. I hope you're following me. All right, now 2 multiplied by 1.008 plus how many atoms of oxygen we have? We have just 16. So we have plus 1 times 16. So therefore, when we add everything together, we come up with 18.016 grams per mole. What this is telling us is that the molar mass of water molecule is 18.016 grams per mole. Here is another example. What is the molar mass of carbon dioxide? Now, whenever you are asked to calculate the molar mass of a compound, one thing they must surely give you is the relative atomic masses of all the elements that are present in that compound. Okay, so now we have two elements present in the compound CO2. CO2 is also called carbon dioxide. It's the gas that you breathe out, okay, whenever you carry out the process of respiration in your body and then you breathe out. That gas coming out of your nose is called carbon dioxide. It's also the gas that comes out of the exhaust pipes of your automobiles, your cars, your motorcycles, and so on and so forth. I can go on and on, but then let's not digress from what we have on ground. So we have carbon. Carbon is 12.01 and we have oxygen 16.00. Now let's start with carbon. We have just one atom of carbon and that gives us 1 times 12.01. And then we have oxygen, which is 2 times 16. When we add up everything together, we end up with 44.01 grams per mole. So that's the concept of molar mass. So now what are the importance or what's the importance of molar mass? Firstly, molar mass converts between grams and moles in chemical reactions. You can use molar mass to convert between grams per moles. For instance, if they give you the amount of a substance in grams and you know the molar mass, you can convert it to number of moles. And we'll be seeing how to do that in a few moments. The next is that it helps us in stoichiometric calculations. Now, let me use an example we can relate to. In the world of money today, there is something that we call forex exchange, or the place where we exchange one currency for another. For instance, now if you live in Nigeria like me and you want to exchange some naira for dollars, then you have to go to somebody who is in my country we call them abokis. Okay, so there is a particular rate, and that rate is not constant, actually it fluctuates, but there is a particular rate that determines how many naira you can give to get $1. Now in chemistry, whenever you want to convert in between units, there are particular rates, only that in this case those rates are constant. So in the real world, when you want to convert money, that rate that helps you to convert in chemistry, one of them is the molar mass. All right, so let's proceed. Converting between moles, mass, and number of particles. Now, using the mole concept, we can convert between mass in grams to moles, and we can also convert between moles to number of particles. Now, look at this first question. When you want to convert from moles to number of particles, either number of atoms, molecules, or ions, always note that 1 mole contains 6.022 times 10 raised to power 23 particles. We've talked about that earlier on while talking about the Avogadro number. So look at this example. How many atoms are in 3 moles of carbon? So the first thing you want to do is to bear in mind that 1 mole of a substance, now in this case we're dealing with carbon, contains or is equal to 6.022 times 10 raised to power 23 particles. And those particles in this case is atom. Now, in this case, now 3 moles of carbon will now contain X particles since we do not know the number of particles it contains. From here now we can now cross multiply. When we cross multiply, X goes to the left and then 3 multiplies 6.022 times 10 raised to the power of 23. Our number of atoms therefore becomes 3 multiplied by 6.022 times 10 raised to the power of 23, and that gives us 1.807 times 10 raised to the power of 24. Now, that's not the only thing we can do. We can convert from mass to moles. Now, let's see how to do that. There is this formula that we can use. The formula says the number of moles is equal to mass of a substance in grams divided by the molar mass in grams per mole. Now, look at this example. How many moles are there in 36 grams of water? That's a question they're asking us. So the first step to do is to calculate the molar mass of water. And how do we do that? Remember, to calculate the molar mass, we need to add up the individual relative atomic masses of all the elements that are present. We have hydrogen and we have oxygen. And that is what has been done for you here in the screen. So we've calculated the molar mass of water to be 18.016. Now, the formula to get the number of moles, remember the question says how many moles? Number of moles is equal to the mass of a substance in grams divided by the molar mass in grams per mole. Now, what is the mass in grams? 36 divided by the molar mass, which is 18.016. That gives us 1.998 moles of water. I hope the class is being interesting. If it is, please go ahead, like this video, subscribe to my YouTube channel so more content like this can get to you. Now, let's move ahead. Using this concept, we can also convert from mass to number of particles. Now, look at these examples. How many molecules are there in 10 grams of CO2? So now the step first, the question says how many molecules, number of molecules or number of particles are there in 10 grams of CO2? So the first thing we want to do is to convert from grams to number of moles so that we can use the Avogadro's number. So now remember, number of moles is equal to mass over molar mass. Now, we have the mass, which is 10 grams, but we do not have the molar mass of CO2. So we have to calculate it. Calculating the molar mass of CO2, which we've done earlier before, gives us 44.01 grams per mole. So therefore, we can now use the formula. Number of moles is equal to 10 grams divided by 44.01. That gives us 0.227 moles. Now, we can now use the appropriate formula of Avogadro's number. We know that 1 mole of a substance is equal to 6.022 times 10 raised to the power of 23 particles. In this case, we're dealing with molecules. So therefore, 0.227 moles will now contain X particles, which we do not know. So cross multiplying, number of molecules will now be equal to 0.227 multiplied by 6.022 times 10 raised to the power of 23. That gives us 1.37 times 10 raised to the power of 23. In summary, the mole concept is a bridge between the atomic world and the macroscopic world. Understanding Avogadro's number, molar mass, and conversions are essential for solving stoichiometry problems and performing accurate chemical calculations. So far, it's been an interesting one. I hope you've had fun on this channel learning about the Avogadro's number and all the other concepts we've treated in this session. Till I come your way next time, my name is David, and all I do on this space is to take the mystery out of chemistry so chemi can make history. If you love this video, please subscribe, like this video, share to your friends, and turn on that notification bell icon so when more content like this come out, you'll be the first to know. Till I come your way next time, stay safe and God bless.